In this lecture, we're going to start with applying previous results to further decide whether a graph with given properties exists or not. So this entire example is something that you can already do by yourself. Pause the video and try these out. These are excellent for practicing both the results we developed last time and one more time reminding yourself of what the terminology is all about. So pause the video, try them out. First up, we have, in a group of 15 people, is it possible that each person is to shake hands with exactly 3 other people? So if you imagine the 15 people as the vertices of your graph, so let's say from 1 to 15, is it possible that every vertex, every person, is connected with exactly 3 other people, sum of the 3 other people? Now remember that the sum of all the degrees of all the vertices in the graph has to be even, which also, as we discovered last time, implies that the number of vertices of odd degree must be even. But here, if every vertex is to have degree 3, it means there will be 15 vertices of degree 3, which means odd number of vertices of odd degrees, which is impossible. So no, this is not possible because there will be odd number, specifically 15, of odd degree vertices. And again, the odd degree here is 3. Is there a simple graph of all vertices of even degree? So this is asking for existence, and therefore an example would suffice to show that there is in fact such a graph. And this is really easy. We can come up with many examples. For example, all even degrees, here's a triangle. Or in fact, any cycle will do, as well as other graphs that might work. In a group of 4 people, is it possible that each person has exactly 3 friends? Why? So friends are a relationship that is what we call reflexive. So if somebody, a vertex, a person, is friends with another person, we're going to assume that they're both friends with each other. So it's a relationship that holds both ways. So we can think of the 4 people such that we can put 3 edges that are connected to every single person. And this is also, is it possible? Which means that if I can come up with an example, it will work for each one of them. So here, if I have 4 vertices and each of them has degree 3, I can see fairly quickly that if I just draw myself a complete graph on 4 vertices, it will satisfy these properties exactly. How many edges does complete graph on n vertices have? So we have n vertices and each pair is connected to each other, which means that n choose 2 is the number of edges in a complete graph for any n. And finally, the question about complete bipartite graph. How many vertices does it have on degree m? How many vertices does it have of degree n? It is always a good idea to create a picture, mental or not, of the graphs, especially if you're given an example with a particular number of vertices. So for example, m and n here, right? So in the complete bipartite graph, we have m vertices in one partition, n vertices in another partition, and all the edges of the graph are present in the middle, okay? So all of these edges are actually there. Everything is connected to everything else in between the 2 parts. So let's see again. How many vertices does it have? We've answered it before, but here specifically, we're asked how many vertices of degree m. Well, the only way to have a vertex of degree m is to have a vertex on this partition because it will be connected to every vertex here, which will of course give it degree m. And that's going to be true for every single vertex in this partition. There are n of them. So there are n vertices of degree m, and exactly the opposite justification works. For every single vertex in this partition, it will be connected to every single vertex in the other partition, giving it degree n, and there are m vertices like that. What is the total degree of the complete bipartite graph? The total degree means if I add all of the degrees all together, and here you can calculate it directly, or you can also remember that the sum of all the degrees of all the vertices in the graph is twice the number of its edges. That is the theorem that we proved last time, the handshake theorem. And we can also recall that we have already proved that the number of edges in the complete bipartite graph is m times n. And now we have to add the 2 that comes from the handshake theorem. And there we go. The total degree of the complete bipartite graph is 2 times n times n. Excellent. Now let's move on to talk about other properties of graphs. And in particular, this time around, we will focus on developing some terminology and results to talk about general ideas of connectivity. So what does it mean for a graph to be connected? Let's start with the motivation. Suppose there are n telephones in a city. What are the possible ways to ensure that there's a connection between any two phones? What is the most efficient way? So let's start with small examples. If we don't know what the general result is supposed to be, and generally we don't, we're going to try to see what we can do with small values for the parameters. So if I have only one telephone in a city, that's a pretty boring problem. It's connected to nothing. So there we go. If I have 2 telephones in the city, of course, the only way to connect them is to connect them directly to each other. But the moment I have 3, I have some flexibility. So let's say I have my 3 phones here. How would you connect them in a way so that there is a connection between any 2 phones? So I can create this complete graph here, but I notice that this is redundant. I really don't need all the 3 edges to connect any 2 phones to each other. If I take away one of the edges, the connection property still holds. This vertex is connected to this one directly. This one is connected to this one directly. And I can get from this vertex to this one through the other one. I just need to make sure that I can in fact connect. So in the old days, old even for me, the connections were established through the operator, right? So your sort of middleman is the operator here that was connecting one person with a phone to another person with a phone. So the connection here doesn't mean direct one-edge connection. It just means connection such that I can go from one vertex to the next, potentially through other vertices. So what about n equals 4? Try this out for yourself. Let's say we have 4 vertices. What are the possible ways to connect all of these together? So let me copy this over because I would like to create a few different scenarios and then see how that would work. Now, again, I'm not interested in creating direct connections to everything. Of course I can, but it's not necessary. So this is, in fact, one way to connect them all. In fact, I can even include this one. This is the most connected that I can get. This is the complete graph on 4 vertices. Everything is connected to everything directly. But if I'm not interested in connecting everything directly, I can, of course, create other possibilities. This graph satisfies the so-called connectivity of the phones problem, right? Notice that for here, I can get from every vertex to every other vertex, potentially through this one. This one kind of plays the role of the main connector. Everything is either connected to it directly, or I can get from one vertex to the other through this. Now, I don't have to have such a central vertex. I could have something that looks like that. In this graph, again, the connectivity property works. If you notice, I can get from one vertex to every other vertex, but potentially through a sequences of other vertices along the way. And we notice that as n grows, this is not, by the way, all the possibilities, there's many others, but as n grows, I am going to encounter not only more and more examples, but also more and more complicated situations where, let's say I give you a graph, are you going to be easily able to tell me whether it satisfies this property or not? So if I have, let's say, something like this, it's going to take a second to figure out whether or not everything is in fact connected to everything else, right? And so the more vertices I get, the more complicated the problem becomes. Notice, of course, that sometimes it's fairly easy to notice if I do have all the possible connections. If I have an isolated vertex, the vertex of degree 0, then this immediately does not satisfy the property, right? So isolated vertices certainly ruin the properties. If you look at the k equals or n equals 4 case here, you will notice that this is not the most efficient way, but I am beginning to see that, for example, for the most efficient way, it looks like 3 edges is going to be enough. Now, it is enough, but it's not sufficient for the exact same reason of the existence of isolated vertices, right? So just having 3 edges does not guarantee that this connectivity property holds, because I could have 3 edges that look like that, and this does not satisfy my connectivity properties. So 3 edges is not a sufficient condition. So we're going to have to be a little bit careful in terms of classifying this connectivity simply in the number of edges. So let's formulate some terminology around this idea of connectivity. You notice that I was using words like we can get from one vertex to the next, and here we're going to actually come up with jargon to describe what this means in terms of graphs. The first one we're going to define is going to be called a walk. In a graph G, a walk from vertex V to vertex W, so let's say here I have vertex V and here I have vertex W, is a finite sequence of adjacent vertices, so the ones that are connected to each other, V0, V1, V2, all the way up to Vk, where V0 is actually equal to V, so I start with V, and Vk is equal to W, so I end with W, and everything in the middle is in fact connected to the next one in the sequence, okay? So this is my V0, this is my Vk, and the walk is a sequence of vertices connected in a row to each other directly, so that eventually I have, let's put it here, let's say Vk minus 1. Let me cheat a little. And it's connected to W. Okay, so this is a perfectly fine walk. Let's come up with some sort of graph where we can discuss whether or not these are walks or not. Okay, so let's say I have a graph on, just to make it a little bit complicated to spot immediately, let's say I have 6 vertices. Let's say I throw in a few edges. So for example, 1, 4, 1, 2, 2, 3. Okay, I'm just making some kind of arbitrary graph here with enough edges to create a variety of different types of walks. Okay, so let's say if I would like to come up with 1, 3 walk, so this is a notation for a walk, this is my V, this is my W, which means it's a walk from the vertex 1 to the vertex 3. Okay, so 1, 3 walk. How can I get from the vertex 1 to the vertex 3 via a sequence of adjacent vertices? Well, let's see. I can go 1, 2, and then I can go directly to 3, right? From 1 to 2 to 3. Perfect. But nowhere in this definition does it say that the walk cannot repeat any vertices or any edges. So I don't have to take the most direct route. I can go for a nice little stroll of a walk. So let's say I can go 1, 4, and then I can go to 5, and then maybe I can go to 6, and then I can go to 2. 1, 4, 5, 6, 2, and then I can end up at 3. Okay, this is a perfectly nice walk as well. I can repeat vertices like I did here. Or did I repeat vertices? No, I didn't repeat vertices in this case. I repeated edges, right? But I could also repeat vertices. So for example, I could go 1, 2, 6, and then back to 2, and then down to 3. So 1, 2, 6, 2, 3 is yet another walk of mine. So it means that my definition here could be a little bit sharpened to clarify whether or not I'm repeating anything along the way. And this is what the other two definitions are for. A trail is a walk with no repeated edges. A path is a trail, so no repeated edges, and has no repeated vertices. Okay, so the walk is the most general concept. A trail allows no repeated edges, and the path allows neither repeated edges nor repeated vertices. So going back to this example here, what I have is that 1, 2, 3 is actually both the walk, a trail, and the path. Okay, it narrows down. So this is the most general. The next one is trail, and the most narrow definition is the path. So if you're the path, you're also a trail and also a walk. Now, if it has no repeated edges, like this one, this one here, then this is going to be also a trail. Okay, this one also has no repeated vertices. So this one is in fact also a path, right? Just because it's not the shortest doesn't make it not a path. I went 1, 4, 5, 6, 2, 3, right? I did not repeat anything. So this one is also a path. And it's the last example here where I have repeated a vertex, right? But I did not repeat edges. So this one is in fact a trail. Okay? Think about other examples of these words being used. Maybe come up with a few examples of walks, paths, and trails on this graph in order to see how to actually utilize those words. Now, a few other things here. A walk or trail or path is called closed if the first vertex is the same as the last one. Okay, so the definitions are exactly the same, but if we also have the edge connecting the first to the last vertex, that's what makes it closed. I went all the way around and came back to my original vertex. That would make for a closed walk or closed trail or closed path, depending on whether or not I repeated edges or vertices along the way. And otherwise, it depends. We can even come up with other words. For example, a circuit is a closed trail. So again, remember, trail is the most general word. So I managed to get from the first vertex to some other vertex and back to the original via some way. Whether or not I repeated anything at all doesn't matter because it's a trail. So in that case, it's called a circuit. I managed to go for a closed walk in my graph. I've managed to go through a circuit. Now, a cycle is a closed walk where all the vertices are different except for the first and last that are the same. So in a cycle, I went from, let's say, again, call it V and W. I went through a sequence of different vertices and I came back to the original, and all of these vertices in the middle are all distinct. So it is essentially a path that connects back to the original vertex. And this is going to be very important in terms of proving coming up results. Okay? Now, particularly for the circuit, for example, notice that I'm not allowed to have repeated edges, but I can have repeated vertices. Whereas for the cycle, nothing at all can get repeated. An interesting question to ask is a question of, for example, shortest cycles. So if I give you a graph like something non-trivial, so for example, well, I've mentioned before that Peterson graph is one of those that you should try on everything else, everybody's favorite first example or counterexample to the result. So if I give you something like this, what is the shortest cycle in this graph? Shortest cycle. Okay? If you stare at this graph long enough, you will notice that it doesn't have triangles. So the shortest possible cycle ever at all is, of course, 3 vertices connected to each other. This one doesn't have any triangles. You'll also notice after staring at it for a while that it does not have any, let's call them squares, okay, cycles of length 4. There's no cycles of length 4. There's nothing. It's very symmetric. There's nothing I can connect in a cycle of length 4. But there is a cycle of length 5. In fact, there's lots of cycles of length 5. This one is 5. This one is 5. There's cycles of length 5 all over the place. So the shortest one is 5 cycle. And in fact, there is another word that graph theorists use. The shortest cycle is called the girth of the graph. So kind of like, how wide do you have to make the entire graph? And then maybe actually you can place all the other vertices in the middle of it. So the girth of the graph is the shortest cycle of it. Here's some other questions to consider that I will let you ponder on your own. What are some of the ways that we can classify paths, walks, and trails? Can a path be closed? Is every path a walk? Can a walk be also a path? Are there walks that are not paths? Okay, so pause the video and try to think of those. This is really to practice your familiarity with the words path, walk, closed, and so on. So can a path be closed? Remember that in a path, I can have no repeated vertices, but being closed means the first vertex is the same as the last. So no, a path cannot be closed. A cycle can be closed. Is every path a walk? Path is the most narrow notion. A walk is the most general one. So yes, if I have a path, it has no repeated vertices or edges, and the walk allows for anything to be repeated. So every path is a walk, but not every walk is a path. So, can a walk be a path? Well, yes. However, this happens only if there are no repeated edges or vertices. So, in general, a walk is not a path. Are there walks which are not paths? Yes, of course. Anything with repeated edges or vertices is going to be a walk, but certainly not a path. Now, let us get to our first theorem in this domain. This one is going to be our standard graph theoretical proof, where a picture will provide an intuition and the familiarity with the above terms will prove to be very useful. So let's see. If a graph has an xy walk, then it has an xy path. So remember, in the walk, I can repeat vertices and edges, and in the path, I can't repeat anything. Now, for the proof, let's think about where we're starting. It's actually going to be a direct proof. So I literally will construct a series of logical connections, starting with the fact that I have an xy walk and deducing through a series of implications, therefore, that it has an xy path. So if I'm going to start with an xy walk, let's give it a name. So let's say that my walk, let's call it P, because it's potentially a path, starts with X, goes through a bunch of different vertices, and gets to a Y. So let's say this is a walk from vertex X to the vertex Y. In fact, to further think about what that looks like, let's come up with a picture. So I have X, and then I have V1, V2, and so on and so forth. A bunch of vertices in the middle, it just keeps going. And eventually, I connect myself to the vertex Y. Here's a walk. If it's a walk, any of the vertices in the middle, as well as any of the edges in the middle, can repeat. And my goal is to prove that I can somehow find a way to get from there to here without any repetitions at all. So how can I get rid of those repetitions? Well, first of all, maybe there are no repetitions in the first place. So that's our first and easiest case, but we do have to state it. So if no vertices are repeated, notice that if no vertices are repeated, then no edges are repeated, then it's already an XY path. It's already a path, and we're done. So I only really have to worry about vertices repeating. because edges, of course, go through vertices. If no vertex is ever repeated, then how could I possibly repeat an edge that involves that vertex? That's impossible, right? So if along the way I already have no repeated vertices, then I already have a path, no issues at all. So the other case is there is a repeated vertex. So we're going to suppose there is a repeated vertex and we're going to give it a name. Let's call it VI. So let's say this guy right here is a repeated vertex. So that means, how can a vertex have repeated itself? So I have my path. It goes X, V1, all the way to VI. And this is the vertex that gets repeated. So that means that from VI, I sort of went on a tour somewhere. I came back to VI, and then I continued along my walk in this direction. Now notice it doesn't say that VI is the only repeated vertex. So this might have happened again. It doesn't really matter. I'm just going to concentrate on what happens in VI. If it's a repeated vertex, it means that I will see it again in my path. Continues on, and then I end up with VK and then Y. So this is my repeated portion. Now on the picture, what that looks like is I went for a little scenic tour here, and I managed to come back to VI. Okay? Well, notice that this is now basically a little appendage, right? So in order for me to not have a repeated vertex, since it repeats itself here, it means that I went through somewhere else and came back to it. I can simply cut this piece out. And that will mean that the vertex VI no longer repeats itself. So this is the part I'm going to cut. Once I have cut it out, so let me notice this on the picture as well. Cut it out. Okay, once I've cut it out, the vertex VI no longer repeats itself. And I no longer have this issue. Now, this doesn't mean I have a path yet, because as I said, maybe there is another vertex that repeats itself and the same exact thing happens. Well, I will fix it in the exact same way as I fixed the issue with the vertex VI. So what we're going to do is we're going to repeat this process of sort of appendiciding the repeated vertex and cutting the portion of the repeated part of the walk out until there are no more repeated vertices. There are no more repeated vertices. Now, of course, this is in fact a finite process because I started with a finite graph and a finite walk in the graph. Once we have done it for all the repeated vertices, there are no more repeated vertices. So once there are no more repeated vertices, what we have is an XY path by definition. Okay, which means we are in fact done. So QED, or some people really enjoy putting in a little black square to show the end of the proof. Isn't this a lovely way to analyze a situation? We started with a walk where vertices can repeat. I think that the picture is really helpful in here because we can see that if a vertex does repeat, we can cut out the piece where it forms a little loop around and repeats itself. Once we cut it out, this vertex is no longer problematic. If we look and find another vertex that was problematic in the same way, we can cut out that piece in the exact same way. Once we get rid of all the repeated pieces, we have ourselves a path from X to Y. Excellent. Let's see what else we can do here in terms of describing connectivity of the graph. And here we first of all get to the actual notion of a graph being connected. A graph is connected if for any two distinct vertices, this is important, being distinct, there exists a VW walk. So if I go from V to W, the graph is connected if I can go from V to W. Not necessarily back to V, so I don't necessarily have a cycle, but for any two distinct vertices, I am able to get from one to another. Now, the previous result that we have just proven says that if I have a walk between two vertices, then I have a path between two vertices. So, in this definition, by the previous result, by the previous theorem that we have just proven, I can replace the word walk with the word path. And then this becomes a little bit more narrow, right? The graph is connected if for any two distinct vertices, I can get from one to another via a path, where a path, once again, means I have no repeated edges and no repeated vertices. So sort of one of the most possible efficient ways. Doesn't say the shortest possible path, but the repetition at least means it's not the longest walk. I wasn't going for a complete stroll all the way around the graph either. Now, if no such thing exists, it means that the graph is disconnected. So let's come up with a few connected and disconnected graphs. So let's say, actually, I'm going to give you a few examples, and then maybe I can give you a minute to think about whether the graph is connected or not. So let's say something like this, or maybe like this. Okay, so here are some graphs. Which ones are connected and which ones are disconnected? Well, this one is connected. I can get from every vertex to every other vertex, potentially via a path. So this one is connected. Same as the next one. I can get from any vertex to any other vertex, potentially via a middleman, but that doesn't really matter. It's still connected. This graph is disconnected because I cannot get, for example, from this person to this, or from this graph to this, from this vertex to this other vertex, even if I'm allowed to use any intermediaries, right? There's just no connections here, direct or otherwise. So this graph is called disconnected. Same with this graph. I cannot get from a vertex in this portion to the vertex in this portion, no matter how hard I try. So in fact, not only this disconnected, we also have another word to describe this. We use these, we call these separate pieces components of the graph. Within each component, the graph, the subgraph that is the component is connected, but the two pieces together are disconnected. Next up is sort of one of my favorite obvious, but actually surprisingly useful results and observations. If the graph G is connected and contains a circuit, remember that a circuit is a closed trail, so no repeated edges, but possible repeated vertices, then we can remove any edge of that circuit without disconnecting the graph. Okay, so if I have a circuit, let's create a picture. So I go from vertex V to vertex, just go around or whatever to vertex W. And it's circuit, which means it's closed. Now, I might have repeated a vertex here, so maybe this actually looks like this. That's totally possible too. In fact, let me just draw in something like this to indicate that I haven't gotten rid of repeated vertices yet. It's a circuit, so I might have these types of appendages along the way. This says that I can remove any edge at all, and still not disconnect the graph. Okay, so what if I cut out this edge? Is my graph still connected? Am I able to get from any vertex to any other vertex? Sure. Well, these vertices are, like the vertices in here are obviously still all connected. It only looks like I might have a problem getting from, let's say, this vertex to this one, because the direct connection between them has been severed. But because it's a circuit, it's a closed circuit, which means that I can go the long way around, right? There's no direct connection, but by the virtue of being a circuit, there is a walk connection between those two. And this is why any edge will work. No matter what edge I decide to cut, this will end up not disconnecting the graph. If I decide to remove an edge in my appendix, this doesn't even affect anything in the middle here, right? But notice that, for example, if I do sever many connections, then I can actually disconnect the graph. So let's come up with an example like that. Let's say I have a little square here, right? If so far it's perfectly connected, and it says if I remove any edge, it will still remain connected. So if I delete this edge, then I am still connected. Now, in a sense, my original graph is connected better or kind of stronger because between any two vertices, there isn't just a single path. There's actually two different paths. I can go there this way, or I can go there this way. Once this edge is severed, there's only one path between any two vertices, right? So after I've cut this out and I've left my 4 vertices, there's only one way I can get from one vertex to the next, but I can still get there, so it's still connected, okay? So this is still connected. However, another thing I notice is that once I've severed that connection and I'm left with a graph that looks like this, one more lost connection and the graph will be disconnected. So one more lost connection and the graph will be disconnected. And this is an important thing to realize. Basically, if I cut too many edges out, I will disconnect the graph. But if I start with a circuit, deleting or removing only one edge will not produce a disconnected graph. And this leads to another really important theorem here. There is a simple path between any two distinct vertices in a connected graph. Okay? I'm going to leave this to you to actually reason out. I think by now you should be able to draw a picture and using this kind of logic, see how to get to this result. There is a simple path between any two distinct vertices in a connected graph. So if I pick some two vertices in a connected graph, that will be the beginning of your proof. Use previous results to show that I can get from one to another via a simple path. So not a walk nor a trail, but an actual path. And next up, we have another result that follows, the fact that the length of a simple path between any two distinct vertices of a connected graph on n vertices is at most n minus 1. Let me give you some motivation for this result. So if I have n vertices, right, and I want to get, let's say, from this vertex to this next one, let's call it V and W. So V is one vertex, and here I have the remaining n minus 1 vertices. The length of a simple path where no vertices or edges can be repeated is at most n minus 1. So the worst possible way to get from V to W is to visit every single other vertex outside of itself. Makes sense, right? I've literally gone through all of the other ones. Now, there of course could be others. What this is saying is at most, so this is my worst case scenario, that I visited I had to go into every other vertex. I had to use every single other vertex as an intermediary before I managed to get from V all the way to W. Makes perfect sense. This also helps when you're looking for shortest paths, and there are a number of different algorithms that you might have actually seen already in your comp sci courses, such as Dijkstra algorithm, where it's looking for the shortest path. And this is a useful fact to know because at most, your length will be n minus 1. So for example, if you're writing an algorithm or writing a loop or writing something like that, you know that if you have exceeded this number, you've already gone too far. You need to adjust. Now, based on this observation above about one severed connection, either disconnecting the graph or not, we have another definition for such a removal. An edge whose removal disconnects the graph is called a bridge. Okay, so this edge is the one that will actually break the graph. Let's take a look at a few examples here. So in this graph here, notice that the intersection is also a vertex itself. If I remove this edge, my graph will get disconnected. this vertex V1 will no longer have a path toward any of these other vertices. That means that this one edge disconnects the graph, and so this one edge is a bridge. If I remove this edge, I can make a very similar justification. It will disconnect this vertex from everything else, which means that it will disconnect the graph, so this edge is also a bridge. So this one is a bridge, this one is a bridge, and of course the other two are bridges in the same way. Let's take a look at this graph here. For example, let's see, is this edge a bridge? If I cut this edge out, will my graph get disconnected? Well, no. In fact, I know exactly why not, because I have a circuit here, or even a cycle, right? So remember that, where is it? If the graph is connected and contains a circuit, removing any edge of it will not disconnect the graph. So I notice that there is a little circuit here, which means removing any of these edges, one, not all of them, removing any one of these edges will not disconnect the graph, which means that neither of those edges are a bridge. However, if I cut this edge out, that will disconnect the graph because it will cut off V2 from anything else. So this edge is a bridge. If I cut this edge out, same thing. If I cut this edge in the middle, it will also be a bridge, right? So this is a bridge and this is a bridge. And I notice not only that no edge in a cycle is a bridge, but also if it holds both ways. If I have a bridge, it must not be in a cycle. So no edge in a cycle or a circuit, more generally, is a bridge. Okay, just to practice this notion a little bit further, take a look at this graph. Which of these edges are bridges? Which ones are not? What other things do you notice? Now that you know this property, how do you start looking for your bridges? Is there some sort of reasonable way to start on that search if you actually want to determine whether the bridges are? We're going to be talking about bridges again in a slightly different way. We're going to be talking about physical bridges that actually motivated a creation of one of the earliest and one of the still most famous theorems in graph theory next time.